Let's continue our theme about the compression of fibrous assemblies. In the end of our last lecture, we describe some structural unit, some brick, which represents a whole fibrous structure which we compressed. We said that in starting position, this brick represents this picture, dimensions x0, y0, z0. The supports are and the force are realized using other fibers in contact, the contact places. And the length between neighbor contact, adjacent contact places is, let's imagine that it is the mean length, which we derived by the ratio K delta, some parameter, by packing density. After pressure of such brick, a lot of new contacts are coming. Because we prefer to idealize the shape of the fiber as a regular shape, we obtain something like this here. Number of contacts is higher now. The height is shorter from Z0 to the length Z. The distance between force and support is now not H0, but the smaller one, H. Number of these segments is higher. Here's pressure P, and the length is delta. The deflection is from value Y0, now this Y. From this picture, we can write a lot of relations. For example, starting volume, total volume of our structural unit of our brick, starting volume, it's evidently x0, y0, z0, x0, y0, z0. Inside of this, the volume of our red fiber is y. Packing density is, V. Fiber volume is V. And we assume that this fiber volume is constant, it's not changed, because the compression represents the smaller volume of air, now the change of volume of fibers. Packing density starting value mu0 is V by Vc0, starting whole volume, so that it is V by x0, y0, z0. In final position, this total volume is same x0, same y0, by the height is now z. So Vc is x0, y0, z. Fiber volume is same. Packing density is V by Vc, so that it is here. And because same fiber volume, we can write that this expression must be equal to this expression, so that mu0 z0 is equal to mu z, or z is z0 times mu0 by mu. Fiber length, which is constant, is or x0 by h0 times delta 0 y. What is the x0 by h0? What is it? x0 by h0. Please don't say me that it is 2. Yes, in my picture it is in the moment 2. But generally it is number of these segments, of fiber segments, between neighbor contacts, yeah? Number of these segments. It is this here, times delta 0. This is the length of fiber. Number of such segments times length per one. Okay? Number of such segments, this, and length per one, delta 0. And the same is valid after pressure. After pressure, it is x0 by h time delta. From the same logic. So that from this equation, h and both must be the same fiber length. Fiber length is not changed. So that h by h0 is delta by delta 0. Length of the bending curve from mechanics. What is delta by delta 0? This delta is this here. This is length of this portion, fiber length of this portion. But based on the results derived by our colleagues from mechanical department, this delta is h times some increasing function y of quantity y by h. So we use it. Delta is h times f of quantity y by h by delta 0, which is h0 times f, this increasing function, same increasing function, but in other point, in another quantity, which is y0 by h0. Nevertheless, h by h0 is delta by delta 0. H by h0 is delta by delta 0, so that h by h0 is delta by delta 0. So that what it must valid that this ratio f y by h by f y0 by h0 is equal 1 in our model. So that this function must be equal this function. And because it's monotone increasing function, it must also valid that y by h is equal y by y0 by h0. So that this is this here, and these relations together are shown here. Nevertheless, delta, the distance between two neighbor contacts, was derived as a k delta by corresponding packing density. So that k delta by mu for delta by k delta by mu 0 for delta 0. So that this is mu 0 by mu. Yeah? And these relations we will use later in two forms. Y is y0 times mu 0 by mu, and h is h0 times mu 0 by mu. Volume of the fiber segment length delta, volume of fiber segment length delta, one of the segment, for example, this segment, or this segment, or this segment, all are same in our idealized structure. This volume V delta is length delta times cross section pi d square by forward is diameter of fiber, equivalent diameter of fiber. Well, number of segments in the compressed structural unit. How many fiber segments are here? 1, 2, 3, 4, 5, 6. Please don't say 6. It's only example in my picture. Generally, how many such segments, fiber segments, are in our compressed structural unit? This number is m delta. It is volume of fiber, V, by volume per one segment. It is well, isn't it? Using equations derived, you obtain this or this or this. And using on the place of delta, k delta by mu, we obtain this here. Only rearranging, nothing more. Yes, we are ready to start with formulation of mechanical relations. We will use so-called energy method. What it means? When I have, I have some rubber for writing with pencil. When I press this one, I do some work. Is it so? From physical work. is work done. So I gave some energy. I must give out some energy. Where is my earlier energy now? Inside of this rubber. In which form? At most as a so-called deformation energy. Yeah? In reality, it is more difficult because some part of my work is transformed to thermal energy, for example, and so on. But the dominant part is the deformation energy. So I can say, in idealized, I will then later generalize it. In idealized model, I can say that my work must be equal to deformation energy inside of this rubber. When I neglect the energy dissipation like thermal energy and so on. Well, this way we will use for a derivation of the mechanical properties. Deformation energy. Deformation energy, we want to find the deformation energy of in one of this segment, because we know this here, it's good to write it as based on the deformation energy of double segment. So deformation energy in one segment, length delta, is 1/2 of deformation energy, which is calculated from this here, from here to here, from between two supports, isn't it? Because this is same than this here. So energy here is, and energy here together is energy here, and we can calculate the energy here, and 1/2 of this, it is the energy related to length delta, deformation energy. So that this is 1/2 of the energy dE to delta. But how it is, back to our picture, how it is with energy. The force started with value 0. It is not one jump to final deflection y. Force was higher and higher and higher. Deflection was also higher and higher and higher. Final position is that we have a maximum value of force and a maximum value of deflection y. Generally, on this way, from starting position to the final position, the deflection will be some deflection eta, some general deflection. And it was starting from 0, and this eta was higher, 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 higher to the final position y. Is it so? Yeah? Well. How is the energy which is now in our beam or fiber, how you want? This is actual force F. Actual force F. We must when I am in some general moment, the beam is in some general moment, some deflection y. Then using the force F, I can a little increase my deflection. Yeah? So the deflection increase to incremental value d eta, which is here. So force times d eta, it's elemental increase of energy, of deformation energy in our beam. Is it so? Yeah. But then the force must be a little higher, because the second d eta, and so on and so on. So that we can write it so, F times d eta, where F is changed to general position eta. Nevertheless, for F, for this force, our colleagues from mechanical engineering derived such equation. It is the equation from our colleague, where it is? Here, yeah? Only on the quantity of deflection I call now eta. Yes. So it is this here. After we must integrate this from starting position to the final deflection y, so that we obtain this here, finally this here. This is the energy per one fiber portion length, delta. How is the total energy? The total energy is energy per one segment times number of segments. So the E delta times M delta. Using this expression, we obtain this after rearranging. After rearranging, we obtain this here. But here is y square, and here is h power 2, 3. Nevertheless, we know what is it, y. For y we have this expression, and for h we have this one. We use it, obtain this here, and after small rearranging, we obtain that the energy is something in bracket, some global parameter, times mu square. Its energy and the final position and the structure have the packing density mu. Thus, on the starting position, the starting value of energy, which was in our fiber bundle or in our structural unit, is E0, and it must validate the same equation with packing density equal to mu 0. That is this here, this is the initial energy, so that the increment of energy is delta E, which is this ratio times mu 0 minus mu square minus mu 0 square. Yes. Now we need to formulate the work done. When I work, it is a process. I have some starting situation, then I give some work, and I finished on a final position in a deformed object. So therefore I must have I will use three type of quantities. Starting value, general value on the way, and the final value. For example, packing density. There are symbols which we will use. Initial value is mu 0, final value is mu, but through our activity, the general value on the way from mu 0 to mu is mu star. Okay? Vertical coordinate, it was z, I call z. Starting was z0, final was z, and on the way was z star. We derived that the z is z0 times mu 0 by mu, and similarly it is valid also this equation. On the place of mu and z, I use the star with superscript star, which are the quantities on the way from starting position to end position. Trajectory, starting value of trajectory is 0. Final value of trajectory lambda is z0 minus z, is the trajectory. And on the way, it is z0 minus z star, because on the way. And final pressure, starting pressure is 0. On the final pressure is P as a function of packing density or of z coordinate, or of trajectory lambda, how you want. Yeah? And on the way, the pressure is P star. So pressure P star is starting from 0 and is higher, the final quantity is P star equal P. The function P star can be formulated as a function of packing density, or as a function of vertical coordinate, or as a function of trajectory. Are the symbols well understandable? I hope a little. Yes. How is the work done now? Same idea. The elemental incremental increase of our work, what is it? is the force times differential quantity of the length. Force times differential quantity of the length. So that, how is the force? The general force on the way. Pressure, for example, P star as a function of lambda, times area, x0, y0 was in our picture, isn't it? Yeah? So that this is force times d lambda star. Yeah? Because some general characteristic of our way through which we press. This one. Now we can 2 times apply some substitution inside of this integral. First is this here, then the second is this here, and finally we obtain work done as a x0, y0, z0 times mu0 times integral, because we need sum these incremental works together. The integral for mu0 to mu from this expression. Nice, here we have the pressure as a function of packing density. It is this function which we want to obtain, relation between the pressure and packing density. So it is a formula for work done. Now how it is the relation pressure packing density? In the mechanic, it's known the term conservative system. Conservative system is a theoretical assumption in which all our work done is transformed to the deformation energy. Yeah? For example, rubber, by the way, is near to this ideal assumption. No one material in the world is perfect conservative system. If conservative system, then the work done must be equal to increase of energy. In the textile, in our fiber assembly, this assumption is not too good, but we need not so hard simplification. We can assume that the work done is proportional to increase of deformation energy. Yeah? So that this C mustn't be equal 1. C is equal 1 for conservative system only, but this C can be higher than 1 so that our work done is higher than increase of energy, because part of our work is dissipate as a thermal energy and I don't know what. Well, so let's use this equation, and on the place of A and delta E we will use our expressions derived earlier. So we obtain A is equal C times delta E. It is this here. After small rearranging, we obtain this. Well, it's nice, but a little not too nice, because our function, pressure as a function of mu, is inside of this integral. What to do? What to do then? Evidently, make some derivative, because it is inside of integral. So make some derivative. Well, let's make the derivative of left-hand side as well as right-hand side. The derivative of this side by mu. Derivative of right-hand side by mu is very trivial. Mu is only here. Therefore, this derivative no problem. Question is, what is the derivative of the left-hand side by mu? Where is mu? No mu star. Mu star is integrating variable. Mu, it is the final variable. Mu is upper limit of this integral. The question is, how is the derivative of integral where the variable is the upper limit? You know, I hope you know from the mathematical analysis that this derivative, this is some expression known from mathematics, that this derivative is this function where on the place of the integrating quantity x now is the upper limit y. Yeah? It's some formula from mathematics. After our lecture we can derive it mutually, very trivial. Well, because this is valid, we can also to solve the derivative of left-hand side. So on the right-hand side, the derivative is this times 2 times mu, evidently, this here. On the left-hand side, the derivative is this function, but on the place mu star, we must write mu. This is this here. Nevertheless, the function P, pressure, general pressure, by last value, the highest value of packing density, our final value of packing density, it's our pressure P. We called it as a pressure P without star, final pressure P. So it's P. So that I obtain this equation here, then this equation here, or this equation here, and when this ratio, which is not function of mu, it is only the function of material parameters, only quantities with subscript 0 and other parameters, constants. If this quantity is called as a parameter Kp, then the result of one-week theory is very easy. Pressure is proportional to mu cube, mu power 2, 3. This is the result of one-week theory from direction to relation of pressure and packing density. 1 week studied how it is now with experiment and was very happy. 1 week worked in South Africa. In South Africa they used wool fibers, the merino wool at most, you know it, and they pressed it to bales, and it was very in good relation to his experimental experiences. So, Heureka, this is perfect. From that time, a lot of people use 1 week's formula. Nevertheless, this formula is not for all packing densities enough well. You can see fast when you will apply this formula to the modeling of yarn internal structure, yarn packing density, and so on, your result wasn't well. Something is not good. Second, let's see how is this equation. P is proportional to mu power 2, 3. So is going over. So that enough high value P represents, Kp is some real constant. So when you use some finite value of pressure, you obtain mu higher than 1. This curve is going so that here from this value of pressure, it's pressure and packing density. For higher values of pressure, the packing density is higher than 1, which is logical nonsense. Packing density mustn't be higher than 1, it's evident. Well, why? In a system, in model of 1 week, which is good and not only for wool fibers, lot other authors checked this equation and they said, yes, this equation is good. For packing densities, 2, maybe 0.2 to 0.3. When your packing density is 0.3 and smaller, then you can say that this equation is very well. But why it is not good for higher values of packing density, which we use, for example, in the yarn. In the yarn we have packing density at most between 0.4 and 0.5, 40 to 50%. Yeah? Why it is possible? Because to solve this problem, to this moment it was pure 1 week theoretical concept, only the derivative is, the derivation of this is a little, I used a little other way how to obtain it. But as a theoretical model, and the result, it is 1 week's model. Because this problem with such model, we derived some generalization of 1 week concept. It is based on following idea. The contact between two fibers is usually not only a point contact. It exists some small area, contact area, between two fibers. And around this, the volume around this contact area functions as a stone inside of, let's imagine it. With this part of my finger I can move with these two, but here it is like a stone. It is some small stone, some granula. So this is some non-compressible volume, isn't it? So that we said to us, okay, it is a non-compressible volume, and 1 week theory is valid. 1 week theory is, well, it's valid, but no for whole volume of fibrous assembly, then in each moment only for deformable volume, which is total volume minus the volume of such stones, which are non-compressible. Can you imagine it? I think principally yes. These non-compressible volumes, in short NV here, all granulas, I call it home granula and granulas. Is it possible to call it here too? So, give following idea. Earlier 1 week's, original 1 week's equation is Kp times mu power 3. Mu is fiber volume by total volume, so both times 3. This equation is this relation to two quantities, P and total volume. Volume of fibers is same practically. Yes, we say no, total volume. We must on this place give deformable volume, which is total volume minus volume of all our stones, our granulas. Symbols. For one non-compressible volume are here, for all non-compressible volumes, for one granula here, for all granulas here. Total volume, total have subscript C, so total volume per one granula is VCG. Total volume of all granulas is W of course, WC. Fiber volume per inside of one granula is WG, and fiber volume in whole granulas is W. Number of granulas of non-compressible volumes is 1 per one granula, and generally N in our material. And packing density inside of our granula, it's very high. It's every time near to 1. But some gaps must be there, and therefore it is we must also have the quantity packing density inside of our granula. It is mu g. It is all ratio WG by WCG or W by WC, both possible. Yeah? Yes. And this is our idea. The problem is now to formulate how is the non-compressible volume of all granulas, the volume WC. Volume, this WG volume, fiber volume inside of our one stone, one granula, one crucible volume is generally say not constant, because do it subjectively with your fingers. By light contact, you can feel that this volume is small, this non-compressible volume is small. Yeah. Also the fibers, volume of fibers, the whole granula is small, so that the fiber volume inside of our granula will be small. Yeah? From other side, when we have some contact which is very intensive, then the contact area is large, whole granula is big, and the fiber material inside of our granula, the volume of this is high. So, volume of fibers inside one granula related to packing density of whole structure. When we have higher packing density, then the volume is higher. So it's some function, increasing function of packing density. It must be so. Yeah? Acceptable? Yeah. Sorry, we have not a theoretical model for this moment. We only know that it is some increasing function. Therefore, in this moment, we will use some empirical function, and we choose the function k times mu power to a. K and a are two suitable parameters. Why? It's evident. If a is higher than 1, then it is convex, increasing function. If mu a is smaller than 1, then it is concave. If a is equal to 1, then this is straight line. So this formula can characterize each existing relation. Yeah, roughly. Nevertheless, this formula is empirical. It is written here, it's empirical. Okay. Using this, the total volume of non-compressible volume of granula is which of number of granulas times total volume of per one granula. Using derived number of granulas, it's same than the number of contacts in our fiber assembly. A number of contacts is a density of contacts, which is this here, times volume, isn't it? Which density of contact is per one volume unit, so times volume. So it is number of granulas, and this is for VCG. After rearranging and using this equation, we obtain that the VC, total volume of all granulas, is given by such equation. The parameter K is possible derive using the idea of limit state, which under this term I think the most compressed fiber assembly. How it is in limit state? The total volume, let's imagine the limit, say the maximum compressed fiber assembly which is possible. No more is possible. Total volume of such structure must be minimum. Sure? Yeah. Packing density is maximum. The maximum value of packing density I will call mu m, and it must be fiber volume by minimum of total volume. That's each definition of packing density. Granula fill total volume of fibrous assembly. Why? Let's imagine it is not well. Then among our granulas must be some compressible volume. If exists some compressible volume, then it's possible this material more compress. If it is possible the material more compress, then it is not limit case. Limit case is that it is not possible more compress our material. Yeah. So in this limit situation, it is so that our fibrous assembly is like as a wall from bricks. One brick, second brick, third brick, and nothing among this. Only stone beside stone. Yeah? Therefore, WC is equal to VC min. And the packing density of this structure, this mu m, is equal to mu g because it's from bricks from our granulas only. It is the wall from our bricks. Yeah? So that our earlier equation, general equation, this here, we can write now in this black form. The red, say what was earlier here. Earlier on left hand side was WC, now on the place of W. VC, W. C on the place of this is now VC min. Yeah, and similar. We substitute all here. From this we obtain this equation so that K is 1 by K nu times mu m power to 1 plus A. We can explain the parameter K as a function of, without other parameters, as a function of maximum packing density. And using this expression here, in our general formula, which is this one, we obtain this here. This is our earlier formula. On the place of K, we use this here. We obtain this. WC is VC times this. And now we can, we have two packing densities here. Maximum value of packing density and packing density inside of granula. We can well imagine that both are same, that inside of granula is every times a maximum packing density. Only a small necessity gaps inside fibers. Yeah? Then, using this assumption, we obtain the W with subscript C is VC times mu by mu m power to 2 plus A. And this we use on the place of our generalized idea. Total volume minus volume of all non-compressible parts. After small rearranging, using the packing density is fiber volume by total volume, we obtain this here, and finally we obtain this equation. Based on our experiences, mu m is usually very near to value 1, maximum packing density, and the parameter A, which is here, based on our laboratory experiences, this A is near to 1. It means this relation is straight. And then we obtain such curve, such diagram. Pressure, packing density. This is our new generalized function, and this is original one-Wick curve. in the region of small packing density, we obtain a roughly same graph, same shape. Then by higher values, our new curve limited to maximum packing density, something which is very near to 1. It's possible to do some approximation because be formally easy, but you can read it later home. I want to comment the relation between our generalized equation and experiments which was doing by Balyasov. Professor Balyasov was earlier known name in Moscow and Moscow Textile Institute. He studied experimentally this relation, pressure and packing density, in very large interval of pressure from 0.0003 megapascals to 328 megapascals. He used for smaller values our braking machines. For higher pressure, he used some special machines from colleague from mechanical department. His experimental results are shown at the point in this diagram. It's semi-logarithmic graph, so that on the abscissa is a logarithmic scale of pressure, on the ordinate is linear scale of packing density. When we use the original 1 week, then from here the curve is increasing so over the value 1. Nevertheless, our curve corresponding to this experiment, it means curve with parameters Kp15, A equal 1, mu m equal 1, is this. You can see that this comparison with experimental results, we compare it. Also, this is experiments by Balyasov, but we have a lot of own experiments from our lab and the same character of results. So you can see that maybe to packing density 0.8, our type of curve is in good comparison to experimental data. Some differences you can see by a very, very high value of pressure and a packing density near to 1, it is here. Why? Because the pressure is so high that quite other physical processes are there. There are the destruction of fibers. It is a pressure which creates from fibers powder. It is a deformation, destruction of fiber material and so on. Therefore, for so high values, but they are unreal to obtain in textile processes. Yesterday we discussed with Professor Ishtiak some research problems, and we both know that the value around 0.8, packing density around 0.8, is the maximum which we can obtain using all textile processes. Higher value, it is the production of fiber boards. It is not textile technology. So you can see that this result is very good, acceptable. We will use it in one of our later lecture about the yarn structure. We will use this final equation. This one here. also as an input to the model of internal yarn structure. To this one now only some short notes. It's possible also generalize this result to two-dimensional deformation, which is schematically shown here. The deformation of fiber assembly in two dimensions, two directions, two decays. And then we, as an approximation, we obtain such equation. It's by a small approximation we obtain such equation. For pressure, for this pressure, for homogeneous stress corresponds also to the compression as shown. Yeah? For homogeneous stress we obtain roughly this equation, which is identical only some other parameter before this relation here. So that therefore is possible this type of equation to use also in yarn by modeling of the yarn, which we will see in our later in another lecture. Well, it's all for today. Thank you for your attention.